Is that working? Yeah. All right, so most of this meeting so far has been devoted to trying to understand at a fixed internuclear distance what happens, how to describe the electron behavior and correlations in molecules, diatomics and polyatomics. So the theme of this talk is more how to go to that next step, how to describe the global properties of the molecule, which does include nuclear motion. Amazingly enough, the nuclei really do move and stuff. And that is often a very non-trivial part of the problem. Okay, so the work I'll talk about and discuss some of what I think of as the successes of this train of thought that I've been following since I got involved in the field, based on frame transformation theory, but also some of the limitations I'll try to point out along the way, and things that I think still need to be improved much more. These are some of most of the collaborators I've worked with in the recent decades of effort in this problem, and in particular, draw your attention to Slava, who's spearheaded our work on H3+ and other polyatomics. So the frame transformation theory grew out of some treatments going back at least as far as David Chase, a 1956 paper. This is one of the first I know about on this general train of thought. I'll try to explain the basic physics of this idea. And others, including Alex and collaborators, and Mulliken and Fano had some important contributions. And it was really developed into a comprehensive theory of molecular physics by Jungian and Dill in for me, one of the most important papers. So Chase, by the way, I guess maybe he was a student of John Wheeler. At least he acknowledges John Wheeler, and I think his PhD was from Princeton. It's kind of interesting because John Wheeler invented the scattering matrix, I believe, looking back into that history. So let me give the cartoon sort of view of where these ideas came from and what's the basic physics here. And I'm going to kind of focus on an atomic example as an illustration of these ideas before moving on to molecules. Because the spirit of this talk is aimed more as sort of a pedagogical overview of these ideas. It's not so much focused on yesterday's hottest results. So kind of the concept is to imagine there's a short-range Hamiltonian part of the potential and a long-range part. And these are usually incompatible. There are different quantum numbers characterizing these different regions of electron motion. Or it could be nuclear motion in a chemical reaction. There are various variants of these ideas. One related idea that some of you may have heard about in the chemical physics community is called the infinite order sudden approximation. There are some small differences among these different theories, which I'll try to make clear. But the basic idea is that we're interested in a scattering matrix. I know a lot of you are kind of coming from the quantum chemistry of bound states, moving into the continuum by making everything complex and getting energies and widths. But we really want more than that in most of what we're tackling. We really want this scattering matrix, the electron scattering matrix off of a molecular target. So there will be some quantum amplitude that you have an electron incident in some particular channel characterized by orbital angular momentum and other quantum numbers and the molecular target eigenstate and so on, and then to emerge in possibly the same or a different channel I. And this scattering matrix, which will be energy dependent, and for a molecule it'll also be dependent on nuclear geometry, is the quantity of interest that you have to get by solving the electron Schrödinger equation subject to scattering boundary conditions. So the idea of the frame transformation is that there is some set of quantum numbers in which the Hamiltonian is diagonal or approximately diagonal at short range, and a separate incompatible set of quantum numbers at long range. And there is simply an overlap matrix connecting these two regions. This is usually a unitary matrix, although in some applications where the actual geometry changes, like in Rydberg states in an electric field, where you shift over from spherical to parabolic coordinates, there are cases where this is, in fact, not a unitary matrix. But this projection controls a lot of physics. And basically, if you want, you can recast the scattering matrix, plug in the unit operator and use the approximate diagonal nature of the Hamiltonian and therefore of the scattering processes in the short-range quantum numbers for the short-range zipping in and zipping out of the electron, out of the atomic or molecular core, and then get a very, what is surprisingly accurate approximation as simply a sum over the diagonal scattering matrix, which is often just written in terms of the eigenchannels, delta alpha of the scattering matrix, and these projection amplitudes relating the long-range channels to the short-range channels. This is the basic physics, okay, and a lot of times we'll write these delta alphas, these eigenphases, and call them quantum defects when we multiplied by pi, using sort of the Seton theorem relating bound state quantum defects to scattering eigenphase shifts. So let me go through an example. This example is in our 1996 Review of Modern Physics article with Mireille Aymar and Eliane Luc Koenig. So for instance, if you take a beryllium atom and pull off an NS electron to very high Rydberg states, say, and it leaves behind the beryllium plus in the 2p state. Okay, well, when you look really, really close to this 2p state, of course, there is a tiny spin-orbit splitting. It's only 6 or 7 wave numbers. Very small part of the physics of the problem, really, compared to the real electron-electron interactions in a beryllium atom. In fact, we know from spectroscopy that for a light atom like this, the real spin-orbit physics is relatively small, but what matters is the exchange splitting is a big energy in the problem, more of the order of 1 electron volt or so. And so really this means that the low-lying Rydberg states are more characterized by these quantum numbers, and the short-range physics, where the electrons are actually interacting and exchanging energy and angular momentum and so on, these are characterized by these LS-coupled quantum numbers. But finally, if you pull an electron way, way away off to infinity, it looks back, it has to see this beryllium plus in a specific fine structure level. Because energy is conserved. If we pull off an electron at this energy, say, it's going to leave the ion in one or both of these states, but in a specific linear combination of those. So anyway, these ideas can be kind of tried to make it more physical by really looking at the potential energy that this electron feels as it's pulled away from the beryllium plus ion. At small distances, the triplet will be more attractive than the singlet typically, and they will have a rather large energy spacing, and then they will more or less come together exponentially. But eventually they have to kind of have split apart and go to these 2 fine structure thresholds. And if you blow them up, eventually it has to look something like this, with huge numbers of Rydberg states below each threshold. And in between there is an autoionization continuum, and above there is a free continuum where the electron just leaves the ion in either of these states. So if you want to make an approximation, you would say the short-range phase is determined by these singlet or triplet quantum numbers. And if you look at the wave function in the different fine structure channels, you see they are locked in phase at small distance. This energy difference between them, the de Broglie wavelength, is so close, they don't feel the difference until you get very large distances, like 1,000 Bohr radii in the case I've chosen here. And so that little tiny amount of physics in that spin-orbit splitting is what changes this spectrum, which you might have near the 2p threshold if there were no spin-orbit splitting. It changes that into this, but just as a simple frame transformation, which says that these outgoing spherical wave fronts in singlet p-odd and triplet p-odd, they simply project their amplitudes according to that frame transformation projection into the different spin-orbit components. It's basically a sudden approximation. Now, the main thing that's different, I would say, than the early formulations of this theory, like by Chase, is that there are closed channels in this problem. Let me come back to here. So when you're, say, at this energy here, when you project a wavefront coming out from the singlet and triplet, it sends amplitude into both of these channels. If you are between these thresholds, then the part that goes into this channel has to reflect back. And then you'll get resonances when you have formed a standing wave in that channel. And that's what all those very complicated resonance patterns were reflecting. Okay, but for this group, we're more interested in electron-molecule collisions. So let's look at the physics here. Now, the time scale for a short-range collision, okay, when the electron is actually coming in and overlapping with the charge and everything of the molecule, maybe feeling the largest multiple moment interactions, this will be of the order of, perhaps as long as 10 atomic units of time, even for a low-energy electron colliding with, say, H2 plus or H3 plus or other more complicated molecular ions. Okay, so it's only around 10 to the minus 16 seconds. It's a very short, in and out. And, but if you're talking about a Rydberg state, okay, the Rydberg electron is going to go off to huge distances, n squared Bohr radii, and it's going to take a very long period of time to do that, around n cubed atomic units of time. So this is a very slow motion, but then each collision is very fast and sudden, and it fits this frame transformation picture very well, this projection of the wavefront going out of the molecule or coming in, projection from the long range to the short range quantum numbers. We have to find the approximate good quantum numbers in order to apply the frame transformation, and this was done nicely in the work by Jungen and Dill for diatomics. Basically, what is conserved during this very fast, in and out, this incredibly short period of time, which is faster than the nuclear motion, really it's the internuclear distance which is conserved. And also, the electron is locked to the internuclear axis, so it's the projection of its angular momentum onto the internuclear axis is conserved. So the short-range quantum numbers are this projection lambda and the internuclear distance r, and the long-range channels, when the electron is far away from the molecular ion, it looks back and sees the molecule in a specific rotational and vibrational level. And so it's the projection of these that is playing the role of the frame transformation in this problem. And the rest can be pretty much carried out analytically. There's a vibrational wave function in principle different for each rotational angular momentum. There is a geometric projection that Fano worked out in 1970, and in other contexts it had been worked out before. But then you can put this together, and it gives an essentially analytical form of the scattering matrix as an integral over vibrational wave functions, the quantum defects that you can get from the potential curves of the neutral system converging to a molecular ion potential curve. Tells you what these are. You can get these from like Kolos-Wolniewicz sort of calculations. And then the rotational part of the frame transformation. And that describes all this interacting Rydberg series going to the different rho vibrational levels of H2+, of which there are huge numbers. They're rather closely spaced, and you get very complicated spectra. In physical terms, I kind of like to think of this picture that you have the different, say, vibrational levels, ignoring the rotational aspect for now. of the molecular ion. You have a Coulomb potential. This is the electron potential plotted versus root r. And you can see for the short-range collision, there are locally open channels, like this one, which are in fact closed at infinity. And those are the ones that have all these resonances. And quantum defect theory describes all that resonance physics essentially analytically. So if you can get the wave function at a fairly smallish distance of the electron, say around here, by R matrix or cone or Schwinger variational calculation, you've got enough information to make this larger S matrix that has closed channels in it. And then by inverting this matrix in the closed channel subspace, you can make the physical S matrix. And this resonates every time there is a resonance in the system. And this gives these incredibly complicated and rich spectra that, for instance, Christian Jungen has calculated. Just to stress a little bit more the physics of this frame transformation from a sort of quasi-classical point of view, if you think an electron is coming in on the ion, this is the electron distance coordinate from, say, the center of mass of the molecule, and this is the internuclear distance in a diatomic ion, say. Okay, if it's in a low vibrational state, there's just a small 0-point motion of the molecular ion. And wherever it hits the core, it's being accelerated. Once it hits the core, it zips in and zips out very fast. But then it reprojects onto all the vibrational levels with this amplitude, which is given by the vibrational wave function. And so if this is a closed channel, it'll go out so far, and then it'll have to be driven back into the molecule. And you'll get all the resonances as a result. And so this S matrix formula is just the linear combination of all the indistinguishable pathways, which comes down to an integral over R and a sum over the lambda values, and these frame transformation matrices. So this is all pretty simple. It's been applied for decades now. This is the famous example from Jungen and Dill for H2, very complicated spectra. The experiment has gotten much higher resolution in the meantime, but this is sort of what the high resolution version of their calculation gives. When you convolve over experimental resolution, it is in virtually perfect agreement with experiment. We applied this to HD photoionization, some regions of complex resonances where there's a low N, low principal quantum number perturber mixed in a high Rydberg series that has this kind of a Rydberg spacing. And these sort of complex resonance features show up all the time in molecular Rydberg states. Very interesting and rich, where they're not simple resonances, they have multiple time scales. Essentially, there's a time scale not only for each little Rydberg resonance to decay, but there's a time scale for the low principal quantum number going to a high vibrational level to decay into the Rydberg closed channel as well, which is sort of this width, and so on. And anyway, this was a nice experiment by Frederick Merck's group, published in 2003. Another big extension that Christian worked on for some years was including molecular dissociation as well as ionization channels, which was quite a bit more complicated, but he found an effective way to do that. And these are some Physrev A paper some years ago with Matskin and Ross, where he applied this method very effectively to H2 and seen the competition between photoionization and photodissociation. So we have set out to apply this to H3 plus dissociative recombination when Slava was in my group years ago. And basically, this is a lot more complicated. You have many more coordinates, and you have conical intersection to deal with the p electrons. You have a Jahn-Teller effect. It's illustrated by these kind of graphs. If you look at the potential surfaces the Rydberg surfaces for the n equals 2, the 2p states, and here are the 3p, and there's actually an infinite ladder going up. There are infinite set of coupled conical intersections that you really have to deal with. And, well, you may not need to really include the infinity, but you really better include up to about n equals 7 to 10 in order to really capture the quantitative physics of this problem we now understand. Based on the treatment we developed at that time, a frame transformation based on the Jahn-Teller interaction coupling mechanism of the electrons and nuclei, we were able to make an approximate treatment that was published in this Nature article and later corrected with an error of pi squared that we had made in misinterpretation of a previous article we took the electron-molecule interaction data from. But it basically agreed fairly well with the experiments at that time and helped to make us confident that the orders of magnitude discrepancy were now understood. This led us to then sort of look at, interpret what was going on, and our interpretation was that the whole mechanism by which this recombination reaction occurs much faster than had been thought before in previous theoretical work is that the electron comes in and, you know, the second it's sort of in the neighborhood of H3+, this equilateral triangle molecule, the Jahn-Teller degeneracy that is associated with the Jahn-Teller effect makes the two in-plane pi orbitals conspire to force the nuclei out of this symmetrical configuration, and it basically, the angular momentum gets transferred into vibrational angular momentum of the nuclei. They're each sort of making their own little circle. But then at that point, if the energy of the electron is really low, the electron can't get back out to infinity again. It's sort of stuck and it has to recollide over and over and over again. And that's the indirect DR mechanism that Holger talked about. And eventually this kind of keeps pumping enough energy into the molecule that it can eventually dissociate. So there's quite a bit of technical development that had to go into treating this problem. Basically, you can think of it, it's a 9-dimensional problem if you treat the 3 electron coordinates and the 3 rotational coordinates of the ion and the 3 vibrational coordinates. And so in a sense, what we're doing with the frame transformation treatment is kind of a divide and conquer treatment. I mean, as usual, we make a Born-Oppenheimer approximation initially to get the electronic eigenstates at fixed geometry. But then we have to fit that to a scattering matrix, or in this case, a reaction matrix that has the Jahn-Teller physics inherently built into it. And that leads to a structure like this, like the Longet-Higgins Hamiltonian, if those of you who are familiar with the Jahn-Teller effect are probably familiar with. So the other thing we had to do was try to deal with all the nuclear coordinates, all the vibrational coordinates, and we used our experience with hyperspherical coordinates to basically convert this into a diatomic looking scenario where we solve the nuclear Schrödinger equation at fixed hyperradii to get, as a function of the hyperangles, to get a set of potential curves. And then we said that the molecular ion is vibrating and moving in this hyperradial potentials with coupling terms. Here it said we used an adiabatic hyperspherical approximation, which we did in our first few papers on the subject, but later that has been eliminated. We include the coupling terms, and so it's an essentially exact now description of the nuclear motion. Initially, we were using a symmetric top model for the rotational degrees of freedom, and now that has also been removed, this approximation. So this is just to get some feeling for what that looks like. When you solve for H3+ in this picture, you get these adiabatic potential curves. The ground state of H3+ sits at the bottom, near the bottom of the lowest one. And you can see near this region, there's not very much non-adiabatic physics going on. Up here, there starts to be some more. This is from my student, Jia Wang, who graduated this summer and worked a little bit on improving the state-of-the-art of these H3+ calculations. And for instance, when he applies that, now he gets sort of at the subwave number level agreement between theory and experiment for these relevant states of H3+. So again, part of this is taking ab initio information. Now, we didn't get this from a true scattering calculation of the type Jonathan Tennyson talked about. These came from Martin Jungian ab initio calculations of the Rydberg surfaces, which were converted into quantum defects as a function of displacements of the nuclei, and then fitted to this form of the Jahn-Teller to get the Jahn-Teller interaction parameters. And that was fed in. I mean, ideally, though, one would really, in principle, one day be able to really take a code like Jonathan Tennyson's or Vince's or Mesa, one of these codes that we've heard about here, and really do an honest scattering calculation for all the fixed nuclei properties. But anyway, using this, we could complete the frame transformation, describe the escape of the nuclear flux for dissociation, basically using either Siegert states or a complex absorbing potential. We've done it both ways now, and in the end, we get more details and more resonance features and so on. This was our comparison with, in 2007, of Samantha Fonseca dos Santos calculations with Slava, looking reasonably good, although still some regions of discrepancy, although at this time we had to use a much higher temperature than the experimentalists thought was relevant. More recently, I guess Holger showed this comparison, that we're starting to look on even more detail on a linear scale and seeing regions where the agreement looks quite good, up to about 0.5 eV, but other regions, very low energy, where it's not looking very promising, and there's clearly work to be done, presumably in theory, but again, the storage ring conditions are also not fully understood, so there's still a chance that some of these discrepancies might be connected to experimental systematics. It's still not completely known. So there's lots we could do to improve on this theory. We could try putting in coupling to other partial waves. We've tried to make back of the envelope estimates of that, and they don't seem to be very important. We still want to try to track where the dissociative flux goes, to predict partial cross sections, to predict angular distributions of the dissociating fragments. And so far, we have not really succeeded in getting that information out of the theory, but I think it'll be an important step, and we hope to do that. Another issue I haven't talked about is this projection, where you take body frame information and convert it into lab frame scattering matrices. This does have one crucial point of uncertainty, which is that when you do the body fixed calculation, you use a body frame energy. Now, body frame energies are not the same as the scattering energies. And so you have to choose an energy to use for your body frame scattering information. And, well, we've kind of developed prescriptions over the years, but this is certainly not an exact science, and it's not clear that this will always work, and there will probably be cases where you have to explicitly go beyond the frame transformation, have to explicitly really solve for the correlated electronic and nuclear motion. But at least for this H3+, everything is very smooth as a function of energy, and it does not seem so important, this energy dependence. But especially in electron-neutral molecule collisions, it seems to be more important. and maybe Mikhail Tarana will say more about that. We've also applied these ideas to other systems, partly to just sort of see if this toolkit we developed for H3+ is working for other molecules as well. One of the ones we treated that there was initially some puzzles, disagreement between theory and experiment, is lithium hydride ion, which is an interesting molecule. In particular, there are these potential curves of the neutral, which there are both excited, and then here's the ion with lithium plus hydrogen. One thing that seemed clear is that there is no crossing of the ion of any potential curve. So it's clear if DR happens in this system, it can only be by this indirect recombination mechanism. So this is one case where we really did use these UK R matrix codes to calculate the quantum defects rather than taking them from bound state information. And they gave these sorts of quantum defect matrices, which are fairly smooth functions of distance. These are versus distance, and fairly smooth functions versus energy. So this gave us some confidence that we didn't need to worry too much about these difficulties about, for instance, the body frame energy. And we could just fold it into the same machinery. It's a little simpler for a diatomic, of course, and it basically gave this kind of agreement with the experiments from the Heidelberg group that were published in 2001, and much better than the old theory. And it also indicated that if we could see that if we took out the coupling of different partial waves, like the amplitudes for an S electron to hit lithium hydride plus and come out in say a P wave, if we left out those kind of couplings, we got something pretty close to what the old theory gave. So that is playing a pretty important role for this particular molecule. And this work with Roman Churik. We could also track some of the physics and found that these complex resonances seem to play an inordinately large role, again, where you have low principal quantum number states embedded in these very high principal quantum number states. These are the most effective regions where dissociative recombination is the fastest. But anyway, part of the reason in co-organizing this whole workshop is that Slav and I have felt that there is still a lot to be done, a lot of problems to be solved. We really need to be able to treat more complex molecules. We need to be able to get accurate electron-molecule scattering matrices for larger polyatomics and for systems where electron correlation is much more important. And you know, to be honest, that technology really needs to be improved from the current state of the art. I mean, it can do a lot compared to what it could do 20 years ago, say, but it still seems very limited, the degree of electron correlation compared, say, to the state of the art in quantum chemistry bound states. For neutral molecule targets, we have a lot less experience with these frame transformation methods. You don't have this big Coulomb acceleration that makes the electron have such high velocity, even for a low energy collision. And so it's still, we've had some successes there, but it's definitely much harder to make the frame transformation theory work there, is our experience, and that aspect really needs to be worked on more. And one fundamental issue about the frame transformation, I know Christian has some ways of coping with this, but I still think it's a fundamental issue that we need to understand better, is that in some molecules you have an ionic potential curve which is very repulsive, like an excited state of, like, say, the 2p sigma u state of H2+, and a lower state like the 1s sigma g. And you know at each internuclear distance you have Rydberg series going to both of those potential curves. So at small distances, if you're near the lowest ionization threshold, the channels going to that 2p sigma are very strongly closed. Like imagine a 2p sigma epsilon d sigma. Okay, you have, you're way below where the 3D energy would be, and that channel should not really be playing a role at all in the physics. But at larger distances, these are coming together, and you need to include that channel. So how do you change? How do you, maybe you need a partitioned R matrix in the internuclear distance and treat the channel as really strongly closed here, but weakly closed over here. This, I still think, is an area that needs to be improved. So anyway, on my wish list is a general code as flexible as Gaussian or MolPro or something like that that can calculate this reaction or scattering matrix at a high level with a high level of electron correlation physics in a balanced treatment of the ion or the target and the n+1 electron system. We also need more experience working with how to include then the nuclear motion. I know there's been a lot of progress by the Berkeley group with MCTDH, coupling multiple potential surfaces together with conical intersections and so on. But again, this I think still, that technology has a long way to go to really treat really rich, complicated systems. And still, treatment of 3-body or more continuum states, either of the electrons or of the nuclei or both, this is still some area that needs a lot of progress. So with that, I'll close and entertain questions.
Your H3 plus data on dissociative recombination, the theory is sort of flat at very, very low energies.
Yeah.
It's flat, and experiments give like 1 over k, maybe 1 over square root of t. But isn't this for rate coefficient? Isn't the general threshold law requires that it should go like 1 over square root of t? So I wonder why your theory doesn't give this.
Yeah, when they write E parallel, there's actually a convolution that's been done. There's a spread of experimental energies, both over the parallel motion as you're merging the beams and on the transverse. And so the transverse has, I don't know, maybe half a milli eV or so spread. The parallel is much smaller. It's maybe 10 micro eV. Sorry? Oh, it's all written here. This was an older one. They've actually improved that now. But basically, even when you're at 0 in the parallel, you still have a spread of energies in the transverse, and that gives this appearance of a wrong threshold law behavior.
So how do you explain the disagreement then? Why the experiment is going up?
I think we have no explanation of that.
It's not just for this one.
It's fairly common.
They all do the same thing. The theory flattens out the experiment.
Yeah, so that's still, I guess, an open question in the whole field, really.
I have a question. You mentioned you looked at back-of-the-envelope calculations about referring to couplings with other partial waves.
Yeah.
Did you mean trying incoming partial waves that were other than P waves, or did you mean coupling to the captured P waves by other angular momentum?
I guess we're just kind of looking at scattering matrix elements to the S or the D, and they seem quite small.
From the P?
Well, I mean, the scattering matrix is symmetric, so it doesn't, I mean, you could come in the P and go out in the D, or you could come in the D and go out in the P. I don't remember which direction. I think we just looked at the scattering matrix elements, which refer to both directions.
Okay, so did you look at coming in an S wave and going out in an S wave?
Yeah, that too. The quantum defect is very flat as a function of internuclear distance, and to get any real action from this frame transformation picture, you need geometry dependence. And the S wave is so flat. I don't know if Slav is here, but that's my recollection, that it's so flat that it didn't seem it could add any torques to the nuclear motion and produce the dissociation. That was our estimate that we did.
Because there have been calculations of the S-wave capture, and the derivative couplings are large.
You're talking about of the Rydberg states,
Yes.
like of the surfaces.
Well, coming in an S-wave and being captured in a non-Jahn-Teller mechanism.
Yeah, I don't remember seeing any evidence of that in our plot of the S quantum defect versus R. So I'm not sure how that connects with your experience. It'd be good to talk about this and see if maybe it should be revisited.
I mean,
When I did it with Yuan, and well, first we did it just plain old directly to the ground state, and that's MCI. With the non-adiabatic coupling, we put in the analytic antibac non-adiabatic coupling and all that. And then Yuan did it up the Rydberg series, and yeah, you got a couple orders of magnitude, so you went from 10 minus 4 to 10 minus 2. And the only way to get it to get big was to actually do something that changed that had a large change on distortion, and that's the Jahn-Teller. So I didn't think that, at least the ones we calculated, weren't huge. And you get really big ones with P's because the P's have the Jahn-Teller and the S's.
but the question is whether it could make up for the small difference between experiment and theory.
But you're still down by 10 minus 4.
What'd you say, the d pi? Yeah, H3 plus though is so compact. I mean, when we looked at where the centrifugal barrier was, and I think Heather Kroll even calculated some of these D-wave quantum defects, and they were very small, I thought.
The ones I calculated.
Also, am I correct in remembering that N equal 40 states are important to somewhere in the
Well, there's a region of rotational autoionization where you see those, but I would say they're not a big player in what determines this physics. In some of the Glosick analysis of Glosick experiments, we thought, at least at one time, that some of those high rotational levels were important, or high principal quantum numbers. I'm not sure. Is that still the case? Do you still think those are important? It may still be playing a role in Glosick's experiments for that three-body mechanism with a helium atom perturbing.
Yeah, Chris, you said that for neutrals, the plane transformation is less justified.
Right.
But are there any major difficulties? I remember a long time ago you tried dissociative attachment case, but I didn't see anything else since then. Are there major
I never did
difficulties?
myself, I don't think, but I know Francis Robichaud,
Yeah, yeah.
when that was his
So
thesis
are there
work.
any major difficulties with implementing plane transformation for this kind of problems, or just nobody did it?
Well, for high partial waves, like say it's a D wave, like a D pi resonance, the low energy behavior is often not as smooth, and you have this body frame energy dependence to worry about, and you also have the strongly closed vibrational channels. And I don't know, Michal, I think you'll talk a bit about this, won't you, in your talk? Show a little bit of your experiences, but it's not clear to us that things are completely stable with respect to changing the number of vibrational channels and so on. We did apply it to the boomerang calculation for N2, some work I did with Christian years ago and Hong Gao, and that seemed, I mean, but almost any theory seems to do the boomerang physics perfectly. So it may not be a really great test. But we don't have very much experience, really.